Hi, my name is Jonathan Alvarez Ariza. I'm engineer professor of the program of Technology and Electronics at the Uniminuto University, Bogota, Colombia, South America. And the idea of this video is to show you some aspects relating to the design and implementation of a CAN bus system and a user interface for the electric vehicle EOLO from two perspectives, technical and educational. So let's get started with the overall aspects relating to EOLO. First of all, EOLO is the first electrical vehicle developed in Colombia by our research group with a patent charging unit through wind. This unit is compounded by Savonius rotors, and this rotor generates a movement in a voltage generator inside the vehicle that charges an auxiliary set of batteries that essentially are the power supply of the different nodes in the vehicle. In second place, our idea with this proposal is to contribute with the electrical mobility or e-mobility in the Latin American region and of course in Colombia. We have detected some lags or deficiencies in policies regarding the electrical vehicles in the region. So our idea is to address in part this type of deficiencies or problems. So the project arose in 1917 in an industrial academic collaboration between two institutions, the Corporación Industrial Minuto de Dios and the University Minuto de Dios. In this framework were proposed two main projects. The first one, a modification in the electrical system in the first version of EOLO, and the second one, a user interface to improve, in this case, the the experience of the driver of the vehicle. In order to meet with the design and implementation requirements, 12 students that belong to the program of Technology and Electronics were engaged in the problem-based learning methodology or PBL through 6 capstone projects, which I'm going to talk about in later sections. Also, as during this period, a second version of EOLO, known as EOLO Pro, was developed. The second version modifies the charging unit system, reducing its size in approximately 35%, which means an increase of the autonomy in approximately 10% in comparison with the version 1. So these are the overall or main aspects concerning the EOLO project. So in order to contextualize you, let me show you some pictures of EOLO in its version 1. So in this version you can see the different slots, and the idea is that the wind enters to the slots and impulses the different turbines inside the vehicle. The movement of these turbines uh, generates the voltage and current for the different batteries in the vehicle. The second version of EOLO has the following appearance. Essentially, you can see that this vehicle is more comfortable and more compact. Also, we have changed the lighting system, replacing the different halogen lamps by LED lamps. And also, we have included some solar panels to increase the autonomy of the vehicle. So continue with the technical perspective. As I described it, two projects, in this case P1 and P2, were proposed. The first project was the design of an electrical lighting system through CAN protocol, and 3 nodes were suggested, designed and implemented. the electronic control unit, and that has the function to communicate the different nodes and distribute the message, for example, for the functions of the sensors that are located in the vehicle. Also, we propose a second node, the front lights, and after node, the rear lights. The second project was the design and implementation of a driver-focused human-machine interface with two screens. The first one, a touch screen, in which the user can command different parameters, and the second screen or tachometer screen, the user can see different signals and variables as current or temperature in the vehicle. At the same time, we proposed a set of sub-projects, for example, the battery balancing, the electrical mirrors and windows, and the electrical mechanisms for the doors. These sub-projects were entirely developed by our students. So in this figure, you can see the scheme or topology that we have followed in our design. So we have choose the SPIC architecture, that is a 16-bit architecture for different nodes. And also you can see the different functions for the lights, for example, light intensity, turn signal, stationary lights, or a strobe. For the front LED lights, we selected the device FL7760, that is a PWM controller. And for the touch screens that these are interfaced through your peripheral with the velocity or the baud rate that you can see in the picture. So with this scheme and the development of the different nodes, the feature of these nodes are the following. First, we have developed an electronic control unit with a small RTOS or real-time operating system known as OSA, with a time slice of 1 millisecond to switch between the different tasks. The first task is the CAN message. The idea is that this task distribute the different messages in the nodes in the network, and the second task monitors the handheld control for the different functions that one user can have. The second feature is that we included a book converter with the device FL7760 that essentially is an hysteresis current control. Third feature is that we included a CAN protocol system with a speed or velocity around 250 kilobytes per second with the standard CAN 2.0b. There is a 29-bit standard that includes a 29-bit standard identifier. Also, the nodes have a low current consumption, approximately 0.6 amperes. And as I described it or mentioned it, the architecture is a 16-bit architecture or with DSPIC devices. These elements compound the new electrical system. So regarding the driver-focused machine interface, we selected two screens, microelectronica HME of 7 inches that are interfaced with 32-bit microcontrollers. Also, for the screens, and specifically for the touch screens, this allows to the user command different options. For example, light intensity, turn on the conditioned air that operates with solar panels, turn on the stationary lights, and test the CAN communication, and by the tachometer screen that I described it show different type of signals. And the current consumption of both the screens is around 0.27 amperes. So these are some examples of the screens um, that we have included. So now let me show you the process that we followed in this case in the development of EOLO. Essentially, our first step was to understand very well the concept of EOLO, and the idea was to communicate the different design requirements or design challenges to the students. Next, in a second step, the students started with the development of the different prototypes in a controlled ambient, in this case in a laboratory. And next, the students implemented and tested the different nodes in the vehicle. The idea of this stage was to observe the robustness of the different elements or subsystems that the students made in EOLO. At the same time, we started with the development of the second version of EOLO. So continue with the process. The students debugged approximately for 1000 hours their designs, the version 1 of EOLO. And next, these models or these designs were interchanged to the second version of EOLO, as you can see in the different pictures. So now let me show you some videos that demonstrate the functioning of EOLO.
Muy good. Descanso abajo. Sí, quedó muy chévere.
So continue with the presentation. I'm going to show you the different technical results with the nodes that we have developed in EOLO. The first technical result is a reduction of approximately 72% in the power consumption of the different nodes in contrast with the first electrical system. The second result is a reduction in the wire gauge, which means a decrease of the cost relating to the electrical wiring. The third result is a robustness in the vehicle communication, in this case through CAN bus protocol. Also, we have incorporated a real-time operating system, a small real-time operating system that occupies around 4% of the flash memory of the DS peak. And the aim of this RTOS is to prevent undesired delays in the functions of the handheld control and in the screens. Also, we have developed a low-cost user interface that gathers both screens, a tachometer and a touch screen, and improving the user experience. So finally, in this section, let me show you a comparison between the first electrical system and the new electrical system deployed in EOLO. Um, you can see the different consumption for the components of the vehicle. For example, the highlights, medium lights, or turn signals, brake light. And in the final row, you can see important reduction of the power consumption in the vehicle. So in the second part of the video, the idea is to show you the different educational aspects entailed with this proposal. So one of the first questions is to ask for the educational context of our students. Essentially, our students belong to the program of Technology and Electronics, and the age range of these students is between 21 and 40 years old. Also, due to the students belong to the program of Technology and Electronics, this type of programs have some difference of the engineering programs. For instance, technological programs seek for the students develop skills or abilities that industrial, commerce, or service sectors need, and the duration of this program is between 2 or 3 years. And finally, the students study in the evening night schedule to 4 p.m. Until 10 p.m. This last element is very important um, because this factor represents a challenge in the way that we constructed the methodology for EOLO, the educational methodology for EOLO. So, as I indicated in the previous slides, we suggested 6 projects, and you can see in the table the projects with their respective description, and the students selected each one of these projects according to their motivations and their learning needs. So at the same time, we followed in the pathway 5 steps. The first step was define the problem, and we decided to divide them by projects in the students in the by capstone projects in this case. The second step was the propose a solution of the problem, and obviously we evaluated with the principal engineers of EOLO the pertinence of each one of the proposals. Third, the students started with the design of the proposals. Four, the students fix the different errors in their proposals. More or less, this step was kind of the debugging stage. And finally, the students exposed the results to the academic community. The idea of this step is that the students shared experience with their teammates, and also the students got a feedback of the academic community. One important element in this sequence is that the students received the educational accompaniment of two tutors for 1 year and a half. So in this picture, you can see the process in the educational pathway. Essentially, the first step was to communicate to the students the different design requirements and challenges, in this case for EOLO. Next, the students started with the different uh, implementations and different designs for each one of the projects mentioned. But one important thing is that the students received a technical training for approximately 4 months in topics pertaining to electrical vehicles, uh, power supplies, embedded system, among other topics. Next, the students implemented and tested each one of their designs in the version 1 and version 2 of EOLO. So at the end of the educational methodology, we decided as educators um, evaluate the methodology, and we made a survey with 18 questions, 12 of them in a Likert scales or closed-ended equations, six open-ended questions. To now, the different recommendations are strong points or weak points in the methodology. And the survey was divided in three sections. So the results are the following. The first result is that the survey demonstrate a good consistency according to the value of the Cronbach alpha. Also, the students evaluated the methodology with a mean value of 4.33 and a standard deviation of 0.78. The evaluation was from 0 to 5. The students indicated that the collaborative learning helped to fulfill with the technical requirements. At this point, it's important to mention that in the methodology we divided or we understand that the collaborative learning is an important factor to uh, get important educational outcomes. So, in addition, the students indicated that they learned concepts relating to battery handling, electrical vehicles, embedded system, among other features or topics. And finally, in this point, the students indicated an improvement of the motivation towards the different topics of theories, essentially towards the learning in the project. In the same way, the principal or main engineers of EOLO assisted the process with the students with a value of 4.5. It's a good value in this case for the methodology. So now let me show you some aspects or critical aspects to improve in the methodology. So the first element is that we need to improve the accompaniment of the tutors in the process. Um, we had a problem with one tutor by time reasons, and obviously these represented a critical point in the development of EOLO. Also, it is needed to improve the process portions because this process can generate different type of delays in the project's schedule. So now you can see different voices that we have recollected or have collected with the survey. So our future work will be focused in new functionalities for the vehicle, for example, a telemetry unit. Also, we want to include some elements relating to the Internet of Things and a sensor cluster. The idea is new students will be engaged in the methodology, obviously improving um, the previous elements that I mentioned it in the presentation. So basically, as you can see, we meet with the different technical requirements, but also we addressed a good methodology in the field of sustainable education. So one of the first conclusion is that the methodology has an important pertinence, and the students participated in a relevant and well-situated project. In this case, relating with electrical vehicles, components for electrical vehicles, and of course, relating to the sustainable development and sustainable education in the field of engineering. Second conclusion is an impact in the learning according to the survey, according to the evaluation of the principal engineers of EOLO, and according to the different observation of the tutors. And these elements demonstrate that the students had a good performance during the development of EOLO. Despite the problems with the tutors or the availability of components. And in third place, a good acceptance and disposition by the students and principal engineers of EOLO towards the methodology. So these are the main constructs relating with the technical perspective and the educational perspective. So finally, thank you for watching this video, and thank you for your time. If you have some doubts, please contact me at this email. And it's important that you observe and you see the paper that contains of the ideas that I mentioned in this video. Again, thank you for your time.